Unit circle. The unit circle is really just using our special right triangles. That is a 45, 45, 90 right triangle and a 30, 60, 90 right triangle. I am forcing these angles on my circle here to be 45 degrees. I'm making it so I'm taking my, for example, my 360 degree circle, and I'm cutting it up into 8s, 360 divided by 8. Each of those angles then are in fact 45 degrees. So all of these angles that I've drawn in here, they're all 45 degree angles. Now this isn't the unit circle in its entirety, it's a part of the unit circle. And I want to look at the part that has these 45 degrees for the reference angle. So recall, a reference angle has to be made, an angle made with the x-axis and the terminal side. So if I was talking about this angle over here, its reference angle would be made with the x-axis and that terminal side. Its reference angle would be right here, which is also 45 degrees. Okay, so that was a quick review of what a reference angle is. In any case, let's look at just one of these 45 degree angles to start with. If I try and connect and make myself a right triangle, because this is trigonometry after all, and these trig functions are ratio of sides on a right triangle. I've just made myself a 45, 45, 90 right triangle in here. Well, on a 45, 45, 90 right triangle, I know the ratio of the sides are 1, 1 to root 2. So that means that this side has to be 1, this side has to be 1, and this side has to be root 2. Oh, and I can multiply that by any scale factor that I want to. The thing is, though, is, well, I want to know quickly what the sine of 45 degrees is, right? That's what this is all about. What's the sine of 45 degrees, cosine of 45 degrees, tangent of 45 degrees? Well, I can look at my triangle here and say, oh, sine. Sine of 45 degrees is opposite over hypotenuse, and on my 45, 45, 90 right triangle, if I'm at that 45 degree angle, the opposite is 1, the hypotenuse side is root 2, so 1 over root 2, got to rationalize it, and I get root 2 over 2. What's the cosine of 45 degrees? Oh, do the same thing, but cosine is the ratio of adjacent to hypotenuse. So the adjacent of 45 degrees is this one to the hypotenuse of root 2, and that's also root 2 over 2. Okay, you can do all that and continue going with tangent and so on and so forth. But it's really annoying to try and have to rationalize every stinking time. So a way that we can make it so we don't have to rationalize it every time is, rather than it being a 1, 1 root 2, I can make that, I can multiply that by any scale factor I want. If I try and force this hypotenuse side to become a 1, that's why it's called the unit circle. That is just a unit of 1 for that hypotenuse, a unit of 1 for the radius, rather than it being a 2, or rather root 2. Well, how would I make this ratio, how would I make that hypotenuse side a 1? Well, the only thing I'm allowed to do is multiply it by any scale factor I want. So if I multiply that by 1 over root 2, which is the same thing as root 2 over 2, I'll leave it as 1 over root 2 for now. Then, how do I want to write that? If I use the scale factor 1 over root 2, then this is going to become, I'll write it all the way out here. Sorry, I'm getting a little sidetracked. 1 over root 2. And I multiply each of these numbers by that. I get 1 over root 2, 1 over root 2, 1. And then if I rationalize this, root 2 over 2, root 2 over 2, 1. Why is that helpful? I just took all of these sides and I divided them all by root 2. So that way, that hypotenuse side can become a 1. After I rationalize these other legs, they become root 2 over 2. Hypotenuse side here is 1. So now, when I say, what's the sine of 45 degrees? Oh, opposite over hypotenuse. Hypotenuse side is a 1. So isn't it just the same thing as the opposite? Cosine of 45 degrees. Oh, cosine is adjacent over hypotenuse. So if I take the adjacent divided by 1, then it's really just the adjacent side. That's why this coordinate, which is located at, well, how do I get here? Well, I have to travel root 2 over 2 this direction on the x, and then I have to travel upward, root 2 over 2 on the y. That's why that x coordinate, it's the cosine of your angle. The second coordinate, or the y coordinate, that's just the sine of the angle that you're working with. And that's true of anywhere on the unit circle. The x values are the cosine of your angle, and the y values end up being the sine of whatever angle it is that you're looking for. So I don't really need to even draw my 45, 45, 90 triangle to tell you what the cosine of 45 degrees is. If I know what this coordinate is, the cosine has to be the x value, the y value has to be the sine of that particular angle. This is true everywhere. Let's look at another location. Let's look at this reference angle of 45 degrees. Draw in your right triangle. Hey, I'd really like it to be a unit circle, so let's force that hypotenuse side to become a 1. These other sides will then be root 2 over 2. Well, because that's still a ratio of 1 to 1 to root 2, right? I've just multiplied it by a scale factor. So the only trouble is to get to this particular point, I gotta go left first and then up. I gotta go left root 2 over 2, so that's not really a root 2 over 2. I'm actually thinking that I'm going left root 2 over 2, or that's like a negative root 2 over 2, and then I gotta go up root 2 over 2. So that coordinate in the second quadrant is negative root 2 over 2, comma root 2 over 2. How does that help? Well, for this angle, which is 180 minus 45 degrees, or that's 135 degrees, the cosine of 135 degrees is, the x-coordinate, negative root 2 over 2. Don't believe me? Look at your unit circle. Here's my reference angle. What's the ratio of the adjacent to the hypotenuse? Adjacent to the hypotenuse. Oh, yes, it is negative root 2 over 2. What is the sine of 135 degrees? Opposite over the hypotenuse. Oh, that's really just that y-coordinate there. Positive root 2 over 2. And I can do this for every one of these 45-degree reference angles. Let's look at another one. 45-degree reference angle. If you don't know what a reference angle is, go back to, I think it's day 5, and look up what a reference angle is. 45, 45, 90, right triangle. We want the hypotenuse side to be a 1. We want the radius of our unit circle to be 1. The sides are the same length. Wait, how do I get to this point? I have to go left, root 2 over 2, and down, root 2 over 2. So I'm thinking about both of those being negative. So that coordinate would be negative root 2 over 2, comma, negative root 2 over 2. So when I ask you for, let's erase that, we're changing the angle. If I ask you for the sine, cosine, or tangent of 180 plus that reference angle of 45 degrees is 225 degrees, cosine of 225 degrees, cosine adjacent over hypotenuse, that's just this x-coordinate. Sine of 225 degrees is just the y-coordinate, opposite over adjacent, or I'm sorry, opposite over hypotenuse. Cool. I can do it for the same thing on the last one. Positive root 2 over 2. Got to go down root 2 over 2 over here. There's my right angle, 45, 45, 90 right triangle with a hypotenuse side of 1. So this coordinate would be located at, got to go this direction, positive root 2 over 2. and then down root 2 over 2. Thus, the sine of, what would that angle be? So now I'm changing it to, I'm just short of 360 degrees. How short am I? 45 degrees short of 360 degrees. So that would be 315 degrees. So I know the cosine of 315 degrees, root 2 over 2. Sine of 315 degrees, negative root 2 over 2. So really, if you just know your 45, 45, 90 right triangle, you're able to calculate all of these trig functions. What is the tangent of 135 degrees? Well, the tangent is opposite over the adjacent. Opposite, so 315 degrees is over here. The opposite of that reference angle is root 2 over 2. The adjacent to that reference angle is negative root 2 over 2. So really for tangent, aren't you just taking the y-coordinate and dividing it by the x-coordinate? Isn't it the same thing as taking the cosines ratio and dividing, I'm sorry, I said that the wrong way, the sines ratio and dividing it by the cosines ratio, which in this case would be negative 1, would be the tangent of 135 degrees. That's true of all of them. So if you want to write down that the x values is the cosine of theta, the y values is the sine theta, and then the y values divided by the x values, that's your tangent of your angle, which is the same thing as saying the sine of your angle, that ratio, divided by the cosine of your angle, which is which is the x coordinates. Right? The sine is the y-coordinates. Tangent should be every time your opposite over your adjacent side. So that's going to be a ratio of your y-coordinate divided by your x-coordinate, which is the sine, y values, divided by your cosine, your x values. How do we deal with the radians? How do I count the radians? Okay, so I'm going to erase all this. Well, maybe not all of it, but a lot of it. How do I count radians? Easy. How many radians is it for half a circle? Pi radians. So what's half of a half circle? What if I cut that in half? Just half of that distance has to be pi over 2. Well, then what's half of that distance? What's from there to there? Well, that's 1/4 of a full pi, right? Don't follow me. Here's a full pi. I need 1, 2, 3, 4 equal pieces. So how much is just one of those? 1/4 of a pi. So I count it by pi over 4. This is really what I do. So here's 1 pi over 4, 2 pi over 4, which reduces to pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, oh wait, that reduces, 3 pi over 2, 7 pi over 4, and 8 pi over 4, oh wait, that's the same thing as 2 pi. On my unit circle, not only do I have these points out here that I need, but I've also got each of these coordinates there on the axes. If the circle has a radius of 1, radius there is a distance of 1. So then where is this coordinate located at? 1, 0. Hey, radius distance is 1. What is that coordinate then? 0, 1. This distance is 1. Where is that located at? Negative 1, 0. And the last one at 0, negative 1. How does that help me? Well, if I ask you what the sine of 3 pi over 2 is, which, by the way, is the exact same thing as saying the sine of 270 degrees. These are equivalent to each other. One's in radians, one's in degrees. So the sine of 3 pi over 2, wait, sine. Oh, y values. I'm thinking y values. What's my y value there? What's my y coordinate? Negative 1. Cosine of 3 pi over 2. Oh, cosine, that's my x coordinate. Oh, it's just 0. What's the sine of pi? Here's pi. What's the y coordinate? 0. Sine of pi is 0. What's the cosine of pi over 2? Cosine, x-coordinate. There's a cosine of pi over 2. Sorry to cough there. What's the tangent of, let's see here, what's the tangent of pi? Tangent of pi, oh wait, tangent is the y-coordinate divided by the x-coordinate, or the sine divided by the cosine, or the 0 divided by a -1 here. So what is the tangent of pi? 0. Oh, well, that's all fine and good, but what about the tangent of 3 pi over 2? Okay, smarty pants. Tangent of 3 pi over 2, y-coordinate divided by the x-coordinate. -1 divided by 0. Oops, I hit a button. What is -1 divided by 0? You can't divide by 0. This is undefined. So tangent is undefined at 3 pi over 2. Or tangent is undefined at 270 degrees. Let's move on to another reference angle. Okay, you're probably a little bit overwhelmed by that, but let's move on to another one and see if you can't catch on. This is trying to get at 30-degree reference angles. So each of these, I'm trying to make them become 30-degree angles. Let's talk about that in terms of radians real quick. Wait, how many radians is 30 degrees? How many radians is 30 degrees? Well, if I know that half a circle is pi radians, and that's the same thing as 180 degrees. How many 30-degree angles fit into 180? Let's see here. 30, 60, 90 degrees, 120 degrees, 150 degrees, 180 degrees for the last one. So there's got to be 6 of those 30-degree angles to make half of a circle. So think about that in terms of radians. If a half a circle is pi radians, then each of these 30-degree angles has to be 1/6 of that. Wait, this is pi over 6. This reference angle here, also pi over 6, pi over 6, pi over 6. How do I calculate how big each of those angles are then? Not the reference angles, but each of the angles. Well, obviously this one's at pi over 6. If that's pi over 6, how much is all of that? Well, aren't I pi over 6 short of a full pi? So that would be 5 pi over 6. Okay, how about if I go all the way to there? Now how many radians am I? Well, I'm pi over 6 further than pi. Pi is the same thing as 6 pi over 6, just reduced. 6 pi over 6 plus another pi over 6, 7 pi over 6. How about all the way to there? Well, I know this is 2 pi. 2 pi, oh wait, I'm a pi over 6 short of 2 pi. 2 pi, I'm thinking that's the same thing as 12 pi over 6 is the same thing as 2 pi. And I'm short 1 pi over 6, so if I was at 12 pi over 6, but I'm short 1, I'm now at 11 pi over 6. So there's each of your angle measures in radians. In degrees, what would they be? Okay, well, this would have to be 30 degrees. This would be 180 degrees. What if I am 30 degrees short of 180 degrees? Well, then you're at 150 degrees. What if I'm 30 degrees more than 180 degrees? You're at 210 degrees. What if I'm at 360 degrees and I'm 30 degrees short of that? Well, now you're at 330 degrees. So talking about the sine and cosine of each of these angles. Sine of 7 pi over 6. Cosine of 150 degrees. How do we calculate all that? Make yourself right triangles using those reference angles. Pi over 6, 30, 60, 90 is pi over 6. Pi over 3 is the same thing as a 60-degree angle. The ratio of sides, 1 root 3, 2. 1 is opposite the 30 degrees. Root 3 is the longer leg, and 2 is the hypotenuse side. How do I calculate the sine, cosine, and tangent of pi over 6? Easy. Sine of pi over 6, opposite over hypotenuse. Oh, it's 1/2. Cosine of pi over 6. Adjacent over hypotenuse. Oh, that's root 3 over 2. That's all this is. But on the unit circle, we're just trying to force the hypotenuse side to be a 1. How do I make that hypotenuse side a 1? I take each of these and I divide them by 2. And then I don't even have to worry about the hypotenuse, dividing by the hypotenuse for sine or for cosine, because the hypotenuse side is 1. So now, using those trig ratios, sine of pi over 6, oh, that's 1/2. Cosine of pi over 6, oh, that's root 3 over 2, technically over 1, but that doesn't change it. So this coordinate here is located at root 3 over 2, comma 1/2. So the sine of 30 degrees is 1/2. Cosine of pi over 6 is root 3 over 2. What if I come over here and do the same thing? Let's see. Opposite the smallest angle, the smallest leg has to be 1/2. The longer leg has to be root 3 over 2. And we're forcing the hypotenuse side to become a 1 because we're on the unit circle. It's still a ratio of 1, root 3, 2. I just took each of those numbers and cut them in half. Oh, wait, but be careful. That should be a negative there. Because to get to this coordinate, I got to move left and then up. So that coordinate on my unit circle, negative root 3 over 2, comma, 1/2. So when I ask you, what's the sine of 5 pi over 6, you would say 1/2. When I ask you what the cosine of 5 pi over 6 is, you would say negative root 3 over 2. Or you can literally draw this blue triangle and then look at the ratio of those sides. Do you notice a pattern going on here? Aren't these two numbers the exact same from there as they is to here, except that the x-coordinate became negative here? What do you suppose is going to change when I move this point down here? They're both going to be negative. What about when I move that point, when I reflect it over the y-axis and move it here? Now what? Oh, well now I got to go positive on the x-coordinate, negative on the y-coordinate. So that's going to be positive root 3 over 2, comma negative 1/2. That happened actually on this previous picture here, right? All of these were, I erased them, go up to 9. Oh, that one accidentally got erased. All of these coordinates, aren't they looking about the same thing? It's just that in the first quadrant, it's positive, positive. In the second quadrant, negative, positive. Third quadrant, negative, negative. Fourth quadrant, positive, negative. Doesn't that work with the x-coordinates and y-coordinates? We're just reflecting the same point over and over and over again. What if I change it up? What if I instead use a different reference angle, a 60-degree reference angle, also known as pi over 3? One, root 3. Oops, oops, oops. The shorter leg needs to be the 1. The hypotenuse side is double that on a 30-69 triangle. Oh wait, but I want the hypotenuse side to be 1. So I'm going to cut each of those in half and get myself a nice, easy hypotenuse to work with. So this coordinate would be located at 1/2 root 3 over 2. What if I reflect it over here? Oh, if I reflect it, then it's going to be negative 1/2 root 3 over 2. When I take that point and I reflect it over the x-axis, it's going to be a negative 1/2, comma negative root 3 over 2. Reflect it again. Positive 1/2, negative root 3 over 2. There you go. There's sines and cosines all over the place. Okay, wait. What about the angle measures? Well, there's pi over 3. We already got 1. So what if I am pi over 3 short of a full pi to get from here to there? Pi is the same thing as 3 pi over 3. I'm 1 short. This has got to be located at 2 pi over 3. Okay, well what if I'm a pi over 3 long, further than pi? Well, 3 pi over 3 plus another pi over 3, 4 pi over 3. Here's 2 pi. What if I am a pi over 3 short of a full 2 pi? Right? My reference angles here are pi over 3's. 2 pi over 3 is, or 2 pi is the same thing as 6 pi over 3, and I'm 1 short, that's 5 pi over 3. Do the same thing with the angle measures, the degrees. 60 degrees. Ooh, why is that so thick? I don't like that. Oh my goodness, I'm getting tons of emails. 60 degrees. Here's 180 degrees. Here's 360 degrees. We know those. Oh yeah, I guess we know the 90 degrees too, and the 270 degrees also. So if I'm at 60 degrees, and I've got a reference angle here of 60 degrees, I'm 60 degrees short of 180, then from here all the way to there has to be 120 degrees. If I'm 60 degrees long of 180 degrees, this angle would have to be 220 degrees. If I'm 60 degrees short at 360 degrees, this is 300 degrees there. So when I ask you sine, cosine, tangent, secant, any of those things of these angles, we should be able to calculate them. That's pretty much what you need to know about the unit circle. I already started talking a little bit about day 8, where we are actually using sine of 330 degrees and cosine and secant of these angles to help us figure out trig ratios. But that's the idea behind the unit circle. What do you need to know and have labeled on your unit circle? You need to have the degrees for each coordinate, the radians for each one. So like right here, there's the radians for this coordinate. There's the degrees for this coordinate. You need to also have the x and y coordinate. Oops, I forgot that on this one. This is on the unit circle, so that radius is 1. That's located at 1, 0. This one's at 0, 1. Negative 1, 0. 0, negative 1. What else do we need that I probably don't have? You need to know the tangent ratios. Tangent ratios is just your sine divided by cosine, okay? That's the y-coordinate. Oh, that 2 got erased. That's the y-coordinate divided by your x-coordinate. You need to understand why we have these coordinate values. I'm telling you right now, if you're just sitting here and you're trying to memorize this picture, and you're trying to memorize this picture and this one, you are never going to make it. Okay, you're going to have to memorize this thing for hours and hours and hours and hours, and then next year you're going to have to memorize it all over again because you need it for trig. Don't memorize this, right? I didn't have any of this stuff memorized. I drew myself a picture. All I needed to know was a 30, 60, 90 right triangle and a 45, 45, 90 right triangle, and I can come up with all of these pictures. Know the quadrant angles. So that means that know what this is. Oh, 90 degrees is pi over 2. And then I add another pi over 2, and that takes me to pi. And then I add another pi over 2, and that takes me to 3 pi over 2. And then I add another pi over 2, and that takes me to 2 pi. What are those coordinates at those locations on the quadrant angles? What are the angle measures in degrees of those quadrant angles? That's what I mean by quadrant angles. Know which trig functions are positive and know which trig functions are negative. In which quadrants? So in the third quadrant, both the sine and the cosine of the angles are negative. In the fourth quadrant, the sine is negative and the cosine is positive. That's true everywhere here, right? In the first quadrant, they're both positive. In the second quadrant, the sine is positive, but the cosine is negative. A way that might help you remember which trig functions are positive and which trig functions are negative in which quadrants. This is quadrant 1, quadrant 2, quadrant number 3, quadrant number 4. I say all students take calculus. What does that mean? What is that helping me remember? All of them are positive in the first quadrant. Sine is positive in the second quadrant. And in the third quadrant, tangent is positive because the sine and the cosine are negative. So when you divide negative by negative, it turns into a positive. And in the fourth quadrant, the cosine is the positive. So that's everything you need to know about the unit circle. Here it is with all 3 of those pictures combined up together in a nice, easy way. know what each of these angles are. Basically, if you get down the first quadrant, you know all the rest of them. If you know that for a 30-degree angle, the ratio of the opposite to the hypotenuse side, oh wait, but I'm trying to, well, I guess I'll do it that way. The ratio of the opposite to the hypotenuse side of 30 degrees is 1/2, then you know the sine of 30 degrees. If you are able to come up with the ratio of 4 pi over 3, recognize what kind of a reference angle is 4 pi over 3. Oh, it's pi over 3 bigger than pi. That means that that's a 60-degree angle. Oh, this is root 3, this is 1, this is 2. So what's the sine of 5 pi, or of 4 pi over 3? What's the sine of 4 pi over 3? It's the opposite to the hypotenuse. Oh, it's root 3 over 2. Oh, wait a minute. The root 3 has got to be negative. Actually, this one was negative 2 because I'm in the third quadrant. Look at all of these y-coordinates here. Positive, 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 positive. Look at all the x-coordinates here. Positive, 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 positive. All of them are positive in the first quadrant. When I take each of these y-coordinates and divide them by the x-coordinate to come up with the tangent, it's still going to be a positive ratio. In the second quadrant, look at all the cosines. Negative, negative, negative. Cosine's negative in the second quadrant. Well, what about sine? Positive, positive, positive ratios for sine in the second quadrant. So sine is the only one positive in the second quadrant. Well, what about tangent? Tangent is the sine divided by cosine. A positive divided by a negative is going to give you a negative number. Third quadrant, all the cosines are negative. All the sines are negative. When I take all of these sines, and all these sine ratios and all of these cosine ratios, then I'm going to have negative divided by negative to give me a positive. So the only thing positive here is tangent. And likewise, cosine is the only thing positive in the fourth quadrant. If you know the first quadrant, you got them all, because in the first quadrant, just each of those points are reflected. Check it out. This point gets moved to here. Then it gets flipped over the x-axis to here. Oh, not to there, I'm sorry, to here. Then that gets flipped over the y-axis to here. What's changing? All the numbers are staying the same, except some of them are becoming negative. It's root 2 over 2. Come a root 2 over 2. That's the easy one. That's pi over 4. Gets flipped to here. Oh, the x becomes negative. And then it flips over the x-axis to here. Oh, now the y-coordinate is also negative. Now reflect that again over the y-axis, and now the x-coordinate becomes positive again. And it's the same thing with the last one. So I hope that was helpful for you. I will look at a lot more of the unit circle on Trig Day 8.